Good morning. For today's lecture, let's do this. Let's do some review of some homework problems. So again, I think this is useful, kind of stepping through this together. You know, so much of these courses involves becoming familiar with the techniques for setting up the problem. So let's do this. So I have selected some problems from chapters 29 and the first part of chapter 30. So let's go ahead and go through these. I hope we have time for all of them. Let's get started. So the first example, I kind of went through and I thought, which are the homework problems that maybe, presenting these in lecture would be really helpful in terms of setting up problems, and I selected problem 15. Problem 15 sounds like this. It says that we have a region where there's a magnetic field. And in that region, it tells us that there is the magnetic field is not constant. Now, what's interesting in this problem is it doesn't tell us the value of the magnetic field. That's not given. So if we're looking for that, we're not going to find it. They didn't tell that to us. But they did tell us this. They told us the rate at which the magnetic field is changing, and that value was 8.65 10 to the minus 3 Tesla per second. So second by second, the magnetic field is apparently getting stronger, so the magnitude is increasing. And so I just drew a little graph here and said, okay, so B is a function of t. I don't really know exactly what the value of B is, but I know that there's a positive slope. So B is increasing. Now, remember that when we're looking for induced currents, one of the ways we can calculate induced currents, we can use Faraday's law. And Faraday's law says when we have accelerating charges, those accelerating charges will create magnetic fields that are changing, and at the same time they'll be creating electric fields. So there are specifically electric fields that get generated when charges are accelerating versus when they're at rest or moving at constant speed, and those are the E fields that we're looking at here. Now those E fields are actually going to become circular, so we'll have a circular E field, and the E fields will create an EMF. So if I've got a loop of wire, for example, here's a loop of wire going on right here, because of the E fields that get set up due to the accelerating charges, I'm going to have E fields set up, and when I integrate along those electric fields, that's what gives us the EMF. So just a reminder, in chapter 29, we've looked at EMFs that are set up due to magnetic forces, and then we've looked at EMFs that are due to electric forces. And those are the only forces. So Faraday's law is not a force statement. It's not a statement of some new force. There's not a Faraday's force. And it's not that the magnetic fields that we're talking about here, the flux here, is not what's pushing the electrons here. It's just that we can show mathematically by looking at the way in which the magnetic field is varying here, we are able to determine how large the looping electric fields will be that are set up along the path of the wire, of the surrounding wire. So it seems like a funny way to do this, but by looking at the magnetic fields here, it gives us enough information. We can determine what the electric field is along the wire, and that will enable us to go in and calculate an EMF. How many volts will we generate within that wire? Kind of remarkable, but that's what Faraday's law lets us do. So we've looked at the magnetic field. Well, the flux is going to depend, let's see if here we go. So here is the flux, and here's Faraday's law. So the EMF that we generate depends not on the flux specifically, but it specifically depends on the time rate at which the flux is varying. So what we need to do eventually is take a time derivative of this flux expression. Now, they told us the magnetic field in this region is uniform, and it's perpendicular to the plane of the loop. Well, that means that in our little vector diagram that I'm drawing out here on the side, I can say, okay, I'm going to pick a magnetic field direction, and we're just going to have that going directly into the page. And then for flux calculations, we have to define a direction for the area vector. And we said that the simplest approach, certainly in this case where the magnetic field is staying constant, let's just set the area vector to be in the very same direction as the magnetic field. What that does for us is it gives us positive flux. If we pick the two vectors to be in the same direction, that means when we take the dot product, we're going to get a positive quantity. So that's what we've done. We've gone back to our detailed formula here. And then we've said, look, the vectors are in the same direction. We can drop the dot product, so the vector signs are gone. And then we can drop the integration, or carry out the integration rather, over the area and get the total area. So this is a simplified formula, and that's going to work anytime we have a constant magnetic field over a given area and the magnetic field and the area vectors line right up. So, you know, you can skip to here anytime you see this in a problem. Now, for the EMF, as we were saying, we want to know what the time derivative of this is. So I actually put a factor of n in here. You know, I always say I forget to count the number of loops. Well, in the problem, they told us that that's not one wire, that's 28 wires. Now, it's not a solenoid. So a solenoid suggests that there's so many wires that the length is becoming an important quantity. But these 28 loops are being treated as if, now it could be kind of solenoid-y, I guess. These 28 loops have to, they can be considered to be following exactly the same path. That's usually the assumption that's made. But you know, once we get to 28, in order for this problem to work, we just have to say that each loop surrounds the same amount of magnetic flux. All right. So I put that in. So I said the flux, actually we're going to count that as N times B times A to get the EMF. So to get the EMF from this, we have to count each one of those loops. Now if I take a time derivative, N is not changing, A is not changing, B is changing. So when we take the time derivative, the only time-dependent factor is going to be the magnetic field. And so the fact that they gave us dB/dt is really helpful because we don't really need B. We need dB/dt. Now, if B is increasing like this, well then flux is doing the same thing. Faraday's law has a minus sign in it. And that tells us that in this case, if the flux is increasing, if that's a positive slope, then the EMF will be in the negative direction. So the directional information we can determine by using the definition of the area vector. Now we talked about that in class. We can use a right-hand rule and a left-hand rule too. So for the area vector, we've defined that into the page. And so if I put my thumb in that direction, then my fingers will curve in the positive direction. Okay, for that. If I put my left hand thumb in that direction, the fingers will curve in the negative direction. You know, my left hand doesn't want to feel left out here. So anyway, there's a left-hand rule, right-hand rule. The right-hand rule, in both cases, my thumb is the direction of the area vector, and the right hand is showing the direction of what we're calling positive rotations, and the left hand is showing directions of what we consider left or negative direction of rotations. So we actually can use those to keep track of the signs. So we've already established from the graphs that the EMF is going to be in the so-called negative direction, and the way we've defined everything, we can determine that that's going to be this direction right here. So that's the direction of the E field being generated by these accelerating charges, and that's going to be the direction of the EMF. All right. So this is, everything we need to determine this. Now we know the number of loops, the minus sign, we've used that, so we don't need it anymore. Notice when we come over and do the calculations, the minus sign's gone, because it's used, it's played its role. It's already determined for us the direction of the EMF, and that's all we use that for. We had to put in the area. Now we could calculate the area as pi r squared. They gave us that information. Watch for diameters. I noticed with almost every homework problem I looked at, they give you a diameter. And I think that's good, because if you're out building something or in your lab measuring something, you usually measure the diameter. The radius is not as easy to measure. But the formulas are in terms of radius, because mathematically it's easier to work with a radius than a diameter. So watch for that. I think the diameter here was 22 centimeters, and I cut that in half, and then calculated the area. So, so I put that in. So there's my 0.0380 meters squared. Watch for units. Make sure units get converted correctly. And then the last thing we had to put in was the dBdt, and that was given. So I plugged that in, and it's telling us that the EMF that we have set up in these 28 loops is 9.20 millivolts, and that's each loop independently would be 1/28th of that EMF. So what's happening is there's a set of E fields that are being set up from these accelerating charges, and every loop of wire that runs through that E field region is going to pick up a certain amount of EMF. So the E field is not independent, but the EMF is. The EMF comes from following that E field through n number of circumferences. I should have calculated the E field here. I didn't do it on this problem, but it's a good exercise to go back and look at. That would be a good problem to put on the midterm, right? Let's see. The last item here, I keep talking about these accelerating charges, and you go, where are these accelerating charges coming from? Well, the accelerating charges are causing the magnetic field to vary. So, for example, it could be that I've got a solenoid inside here, and that I've got a bunch of wires, and those charges, the current is picking up speed. So as those charges accelerate, they will generate an electric field that goes in the opposite direction. So we talked about this in lecture, and that's what's happening here is this magnetic field indicates that there are charges somewhere that are accelerating. And it's the E fields being, in this case, it's the E fields being generated by those accelerating charges that are creating the EMF. I guess we've said it all, right? Okay, so again, Faraday's law, it's not that the magnetic field here is exerting a force on the charges out here. It's that by watching the magnetic field, we can determine what the electric field will be in the region where the wire actually is. Okay, I hope that makes sense. Let's move on. We don't want to spend the entire time on just that one. Oh, we still are on the same problem. Sorry. Let's see. So what do we carry over from the page before? Well, the 9.20 millivolts, that's about it. Because here what they're doing is they're asking how much current will this set up. And what we've determined is the total EMF running in that circular direction along that 28 loops of wire. We want to find out how much current it's going to have. And the current will depend on how much voltage and how much resistance. Well, EMF is just voltage. So we know what the voltage is here. The voltage is whatever that EMF number was. So you can see now that I've got, this is V, driving the current. We just need to find out the resistance. So whatever the resistance is, that's going to help us determine how much current we've got. So to get resistance, we're going to do a resistivity. They told us it's made out of copper. There is the resistivity for copper. We need to determine the length. The length is going to be 28 loops of pi. Now that is the diameter. So for the circumference, I did pi times the diameter. And that says that we have a combined 19.4 meters of wire that is in these 28 loops. And that's going to contribute for the resistance. Now Now, what's happening here then is, let's think about this. How does this compare with a circuit that has a battery and a resistor? Well, in this case, the voltage that's being generated is everywhere. So the voltage is at every location. It's not isolated in one place. The E field that's being set up is equally, has the same value all the way around those 28 loops. So it's a battery that's distributed uniformly through that 28 loops, and so is the resistance. So that's kind of an interesting effect that's going on here. The resistance, what else did we need? A cross-sectional area. Now remember, this is the cross-sectional area of the wiring itself, of the wire. So the wire is going to be tiny, right? They told us the wire has a radius of, oh, I hope that was a radius and not a diameter. Yeah, it looks like the diameter. Check and see if I got this copied right. I hope I did. Because that would make the diameter 2.6 millimeters, and that's a pretty thick wire. But I'm treating this as if that's the radius of the wire itself. It's pretty tiny. And that would give us 5.31, 10 to the minus 6 square meters for the cross-sectional area. Anyway, overall, I ended up with 0.0612 ohms. So I'm going to get something in ohms. And that resistance, again, is uniformly distributed through every length of that 28 loops. All right. So I put that in, and it's predicting that with the EMF we calculated, we would be getting 150 milliamps of current throughout this, these 28 loops. Now, as far as the heating effect, what they're asking about in the problem is, you know, I've got these loops, and we're going to place the loops next to some accelerating charges where there's a varying magnetic field, and that's going to cause the wires to heat up. Oh, well, it's going to cause the current to run, and that current running in the wires will cause the wires to heat up. So we can go back to P is equal to V times I, R times I squared. Either approach should work, and we're getting a power of 1.38 milliwatts. Now that's not going to heat up much, but there you go. There's a certain amount of thermal energy being generated due to the resistance in these 28 loops. All right, so a good problem. I like that problem. Here's another problem I like, problem 29. Again, it's an induced current, and let's see how this works, because this time we're inducing the current not by using electric forces from accelerating charges, but we're using magnetic forces. So it's a little different way that we're inducing the current here. This is kind of the first introductory example, or one of the early introductory examples in the chapter that we worked from. We said that we could have a conducting wire shaped something like this, and we could have another conducting piece of something running along those wires so that they're maintaining electrical contact here. And then here, there's the magnetic field. Now, you can tell this is the textbook's magnetic field. It's coming out of the page. My magnetic fields always go into the board instead. But they say that this wire is being pulled at a steady speed, 1.3 meters per second. The length of that wire within the magnetic field region is 25 centimeters, and that the magnetic field strength or magnitude is 0.350 Tesla. All right, those are the numbers we need in class. We derived an expression showing that when we move a bar through a magnetic field, well, we already know from chapter 27, there's going to be forces on those electrons. So last problem we were looking at, it was an electric force that was pushing the electrons. This problem, it's a magnetic force that's pushing the electrons. So we can use either. So magnetic forces are going to be pushing electrons this way, and that means officially the current is this way, and officially the EMF is opposite to the direction the electrons are being pushed. I apologize, I didn't make, it was, talk to Ben Franklin, who originally defined positive and negative. It was kind of a coin toss. It could have been either definition. We could be saying electrons are positive and protons are negative. Anyway, it's not such a big deal, I hope. Also, I went ahead and put a force in here because in the problem they ask us to calculate how much force would be needed to keep the bar moving across the magnetic field region, and that's something we talked about in class. So we are going to need a force. If there's current running through this system, we are going to need a force to keep it moving. If there's current being generated, what's going to happen is this. There's two steps here. So what's happening, let's think back in terms of the electrons. So the electrons we said are negatively charged, and if we pull the bar through the magnetic field region, the electrons within that metal bar are going to experience a force in this direction. I'm using a left-hand rule for this, something like that. And the force on the electrons will be here. That means that the electrons will start moving. When the electrons start moving through the wire, well, then there's going to be a force on those moving electrons. Now, remember, if the electrons are moving here, we define the current in this direction. And we also have forces that tell us how much force there will be on a length of current. And that's the formula we're going to pull out and use here. The force on a length of current I traveling through magnetic field B, there's going to be forces all along here. That's the net effect going off in that direction. And that means that we're going to have to pull with an equal amount of force if we want it to keep traveling at a constant velocity. And that's the plan. We want this to keep moving at a constant velocity, so we're going to have to pull this at a speed that matches the force on the other side. If we pull it with more speed, at least initially, it will start to accelerate. So this is the force that we're going to have to pull with. We're going to have to pull with V. Looks like we have now B squared, L squared, and R. So, and where did we, oh, I guess we did it this way. So, let's see, the EMF we got, VBL, speed, magnetic field, length, that gave us 114 millivolts of electric potential that we could work from. The current is E over R. Now, in this case, they just flat out told us the resistance. So, we didn't have to go back and calculate that. And what's kind of interesting here, too, is maybe it's just at one point. Or, in any case, this is the 27.5 ohms of resistance. We can use that, the voltage and the resistance, to determine the current. And then once we know the current, we can calculate how much force. It's not much force, so this is not a big, powerful generator of any type. We're only generating a voltage of 114 millivolts, around 1/10 of a volt. The current we're generating is only a couple of milliamps, and the force we need to keep it moving, 362 micro newtons. So tiny, a millionth, a few hundred millionths of a newton. Now we're assuming that everything else works frictionless. So we're saying that dragging this bar across the the electrical conductors, there's no friction. It doesn't require any additional force. We're only taking into account that magnetic force working opposite to us. So anyway, another good example. I think we've got one more that's similar. Let's take a look at maybe this one. So what do we have here? So it's kind of the same setup. I have a metal conductor here, a couple of rails, and we're going to let another metal bar slide along here. And somehow it's frictionless, right? We have this ultimate frictionless lubricant that is going to allow this bar to just slide across the top. And what we're going to do is we're going to give it an initial push. Now, what they say in the problem is they're going to disconnect. There's a wire that we can connect on the end to complete the circuit. But what we can do is we can disconnect that. If we disconnect it, then this thing slides across at the same fixed constant velocity because we're assuming there's no friction and there's no force slowing it down. But what we want to do then is we want to go back, still give it that initial velocity, and then at, I'm going to say t equals 0, we connect the circuit. Now, what happens once the circuit connects? Well, then we can start driving current through those wires. The EMF is there the whole time. So as long as the bar is moving through that magnetic field region, there will be an EMF generated in that bar, in that metal bar, from one end to the other. So the EMF is going to be V times B times L, and the current then is going to be the EMF divided by the resistance. Ooh, let's see. Oh, they didn't give us any numbers. Or at least I guess I didn't. There are no numbers. So everything here is just going to be symbolic, just going to be algebraic symbols. So that big R is the resistance. And let's see how this, here we go. Same force formula as we saw in the last problem. So what's happening this time is, here's this bar, and it's got a velocity in this direction, but there's a force opposing the direction of velocity. The effect on that is going to be to slow things down. What's happening then is I'm going to have a velocity in this direction, because I gave it a push, but there's going to be a force opposite that's going to create an acceleration. And that acceleration is going to slow this down, and well, eventually is it going to have it stop? So we have to find out if that's the case. Because what's going to happen here is this. As V gets less and less, the force reduces, and that means the acceleration also drops off. Let's see what happens. If we follow the formulas that we've outlined so far, they should be able to predict whether this will ever come to a complete stop or whether it's just going to keep moving forever. Yeah, kind of fun, I guess, to ask that question. So let's start with the definition here. Acceleration, dv dt. That's just kinematics. So that's our kinematic definition of how time and velocities and accelerations are related. Now, set that aside, and what we want to find is, well, what's going to determine the acceleration? And the acceleration for this setup is going to be force divided by, it's always the case. This is our force. This is our mass. And there's a minus sign in here to remind us, no matter how we define our coordinate system, acceleration is always going to be opposite the direction of velocity. So if v is a positive number, that minus sign makes sure the acceleration is negative. If v is a negative number, that minus sign makes sure the acceleration will be positive. So however we define our coordinate systems, that formula seems like it works. Okay, and that's a good check. That's something you should check in your formulas to see if you need a minus sign or take one out. Sometimes you have to put in absolute value signs. You have to play around with the formulas to make sure that physically we have the right relationship between what direction is the velocity and what direction is the acceleration. And I think we've got it on this one. So now we're ready to set things up. What we can do is this. We're going to take dv dt and substitute in for the acceleration. So now we are going to bring these two formulas together. This is only kinematics. This is telling us about forces and mass and how they will create an acceleration. So let's merge those together. Now I have a factor of v on this side. That can be brought to the other side. It's going to show up in the denominator. The dt that we have here, we're going to bring over to the other side of the equation, and then we're going to integrate. Okay, so that's a very standard approach. We've done this many times before, I want to say, during the course of Physics 4a and 4b up until now. And so now what we're ready to do is integrate both sides, and then we want to set limits of integration in a way where they match. So what we're going to say is at t equals 0, there's my graph over there, at t equals 0, the velocity is v naught. And at t, some later value of t, we will be traveling with some later value of v. So the v and the t, these are going to be variables in our final formula These are fixed. The 0 here and the v naught here, those are fixed quantities that we've defined from the outset. Now, there's too much stuff going on. There's too many constants here. I did the integration, and what I got was the ln on this side. I got the ln of v between v and v naught, and that gives me the ln of v over v naught. Now on the other side we've got a lot of constants, so what I did was I defined a time constant. All through the course, all through circuits, we've had time constants. I think we first introduced them in RC circuits. So, and then we also had, maybe that's the only place so far. We're gonna continue to define time constants. The time constant here would be whatever there is out front of the time, but we have to invert it. So we want to define it this way, minus t over tau. So that saves us space. We're not writing all those variables down. What we can do is just say t over a time constant, and that means by looking at the formula, it's a time constant depends on the mass, depends on the resistance, the magnetic field, and the length. So those are the values that are going to determine what that time constant will be. Now if we go over to our graph, a time constant, what we know is going to happen here, at least this is what we're predicting, we're going to have a speed that slows down. Now it's not going to be a linear effect, because what we said is as it slows down, the force will also decrease. So those are going to be dropping together. And so what we want to do then is draw a graph with a curve to it here. And a time constant is going to bring us out here. So down to where it's dropped to 37%. I don't know if that's the best exponential to draw. But the time constant will be, this much time, something like that. And that's what it's going to depend on. So that's our formula. V is equal to v naught e to the minus t over the time constant, and this determines the time constant. So let's ask what happens. What happens if there's more mass? What if we do this with a bar that's heavier? And I'm thinking, something that's heavier, that's going to resist the slowdown. It's harder to bring heavy objects to slow them down. And that's what we're seeing, for example. If the mass is twice as much, it's going to have a time constant twice as large. It is going to take twice as long for this thing to slow down. Now we had asked the question, so here's our exponential function, and that was my attempt at an exponential graph. Not my best, but it's not bad. What we also asked was this. We said, look, is this thing ever going to slow down completely? And you go, well, if it's truly, truly frictionless, and the only thing slowing it down is this magnetic force, then no, it never completely comes to a stop, because you can see that this never quite drops to 0. Well then, if it never quite comes to a stop, is it going to travel an infinite distance in any case? And to check that, what we can do is take this velocity formula and replace the v with dx dt. So if we take dx dt and set that equal to this expression for velocity, we can do another one of these integrations. So I kept the dx on the left side, took the dt over to the other side. This time the left of the equation is just integrating from 0 to some x value, dx. That's going to give us x. And on the other side, we have to integrate this exponential. So I integrated the exponential, and integrating that brought in a factor of tau. And then there was a negative sign, but I got rid of that by switching limits. Instead of 0 to t, I'm going from t to 0. And this is what I ended up with. I ended up with, as a function of time, where will this be located? And, well, let's see. Let's try it out. If I put t equals 0 in here, then it starts out, that would drop to 0 at x equals 0. If I put t equals infinity in there, you know what it says? It says that it asymptotically approaches the value of v naught times tau, whatever those happen to be, but it will never cross that location. So this is one of those examples. I think we saw this back in Physics 4A when we were looking at resistive forces in fluids back in Chapter 5. What we find is that even though the mathematics predicts it never quite comes to a stop, well, it's slowing down enough that it doesn't travel an infinite distance. It just gets closer and closer to this final location, but it never completely comes to a stop, which is kind of cool. And so it's never going to cross. It's going to asymptotically approach. This is not labels, I'm going to lose points on that. This is x versus t. And it never crosses the value of v naught times tau, and I'm calling that x naught. Anyway, kind of interesting. If it's pure magnetic deceleration, no frictional forces, it's going to get closer and closer to that point, but never quite reach it. All right. Here's a favorite. Problem 37, this is a generator, and if you remember back, we used the example of where we had a magnetic field here, and we used some kind of mechanical energy device, maybe it's a wind turbine, something like that. So I got a wind turbine, and it's being used to turn loops of wire through a magnetic field region. This is the number of loops. That's not north, that's the number of loops. Here is the magnetic field lines. In this case, they're running across the page. And as we turn this around, we have derived a formula that said the EMF that would be generated. So I think we used, pretty sure we used, well, you could use either one. You could use Faraday's law, or you could just use the direct magnetic force approach, which maybe is better. We had solved this as NBA omega cosine omega t, where A is the cross-sectional area of the loop, B is the magnetic field, and N is the number of loops. Now, they said we're designing a generator. It's going to have square loops, and they're going to have a length, 5.15 centimeters, and so the cross-sectional area of each one of those loops, 2.65 10 to the minus 3 square meters. So we've got the area. It says that we want to spin the generator at 60 hertz. Well, I got to get that converted into an omega by multiplying by 2 pi. That's 377 radians per second. So 60 hertz is like standard AC that we plug into in the outlets in our homes. And that's at 377 radians per second. What else do we have here? Oh, the magnetic field was given. They just want us to be able to go in and solve for N, and that's what I did. So this is what the peak value of EMF would depend on. And remember, this is an AC generator, so I have this very nice cosine or sine function, whichever. Since it's a cosine function, all that really means is that I'm defining maybe this is t equals 0. So for this purpose, cosine or sine are kind of interchangeable, unless they tell us something about when t equals 0, where are we? And so, maybe we're here. That's a cosine function if t equals 0. Maybe we're here. Maybe t equals 0 is here. But the values run between positive E naught and negative E naught. Those are the voltages. All right, and the number I ended up with was 57.2 loops, and so there you go. And yes, I guess you could find a way to have 57.2 loops, maybe not. But that's it. That's our generator problem. So I'm going to move on from that. And then here is our transformer problem. So transformers are really cool devices. Maybe I mentioned this in lecture. I was surprised years ago when they started having a whole series of hit movies about transformers. I mean, transformers are really cool, but I just didn't think it would have that appeal at the box office. But anyway, I never saw any of those movies, but I guess I should have, because they're about transformers. So transformers, we said, have N loops on each side. There's a primary side, secondary side, and we said the properties we want to keep track of here are numbers of loops, voltage or EMF, current, and power. Now, transformers are simple enough devices that we can build them so that they're basically 100% efficient, which means no thermal energy is generated, and that means that the electrical energy provided on the primary side is matched by the energy that has transferred successfully to the secondary side. So we'll set the P1 equals P2, we'll say it's an ideal transformer. Now, for each side of the transformer, P is going to be equal to V times I. So whatever the voltage drop is across those loops times the current, that's going to tell us the power coming in. And then on this side, same idea. The voltage across those loops times the current will tell us how much power we have successfully transferred. Now, for this, you really just have to be given a few numbers to start with, and then you can run through all these equations. Now, in this case, they told us that the power of the secondary or primary doesn't matter because the power is going to be the same. So P1 and P2 are going to be 75 watts. That's the power at which this transformer happens to be operating at a particular instant. And it says that on the secondary side, the voltage is 12 volts. Well, that's enough information on that secondary side. I could calculate the missing piece of information. And the missing piece of information was the current. It says that on the secondary side is 6.25 amps of current. They also told us that the current on the primary side is 22 amps. And so that was enough information. I could solve for the voltage. So the voltage on the primary side, 3.41 volts. So now what I got is I've got the V's and the I's and the powers on both sides. Now what they ask us is this a step down or a step up transformer? And step up and step down is defined in terms of the voltages. So they just want to know, is the secondary higher in voltage or lower in voltage? And we can look at the numbers and see that the voltage actually went up. This is a step up transformer, and it went up by a factor of 3.52. Now they didn't ask this, but what it tells us is that the ratio of the loops matches the ratio of the voltages. That was kind of the foundational formula that we developed in lecture to describe how transformers were operating. So to build this transformer, I would need to make sure that side 2, compared with side 1, that ratio is 3.52. So I've made up some numbers. Let's say that N1 is 100 loops and N2 is 352. That would work. That would give us the 3.52 step-up factor. Questions on any of that? And I promise I'm going to get to that. I'm going to get those Transformer movies watched. I just haven't gotten around to it yet. I am looking forward to full-length features about Transformers. Transformers are awesome. All right. Those were the chapter 29 problems. So we're going to move on now and take a look at some problems from chapter 30. As I keep saying, chapter 30 is really 2 chapters. And so we're going to look at the first half of it in this lecture, and we are going to save the last half of chapter 30 and 31. We'll include chapter 31 in another set of in another review lecture. We split up 30 between the 2 review lectures. And so what this is looking at is it's looking at the inductance part. They have, if you remember, in chapter 30, we introduced these devices called inductors, and we want to find out what are voltages across an inductor, and specifically, what I want to find out is how can we incorporate the idea of a voltage drop. We talked about voltage drops on resistors. We've introduced voltage drops on capacitors. I want to have a voltage drop for an inductor so that all of the different devices we've looked at for circuit building have matching formulas. There's analogous formulas that we can work from. So here is our symbol for the inductor. Here is the typical geometry for inductor. We said that typically is a solenoid set of wires that works very effectively. It generates a lot of inductance. And the inductance value that they've given us in the problem is 280 millihenries, and henries are like the best unit ever defined. So remember, the way the inductor works is this. We have current going through this wiring. So I want to show what's going on in the wiring here and here, kind of a review of what we talked about in lecture. And that is, let's see, in this particular problem, they said the current is dropping down. And again, they didn't tell us what the current was. They just told us the rate. This is kind of like that first magnetic field problem we looked at this morning. And so di dt is equal to, it's a little different. They told us that we dropped from 25 amps to 10 amps. So they did tell us. I take that back. So the di here is minus 15 amps. The current dropped by that much during a time interval of 0.360 seconds. That gives us a negative 41.7 amps per second. And that's a rate at which the current is coming down. So it's decreasing by that amount every second. Now, all right, so coming back to our solenoid, so I got current running through these wires, and let's say it's running in this direction, but it's slowing down, or it's decreasing. So what we can do then is say that I is in this direction, but di dt is opposite. Now, we had done this in lecture, I think. We said that one way to think about current, it's, oh my gosh, what did I do here? Oh, I really did. Okay, sorry about this. This needs to get changed. That is a T. So this is dq dt. That's a T. I know it looks like an S, but it's really a T. And that S right there, it's another T. Sorry about that. So I have to make a note here to get that changed before I post it. So that's a T, that's a T. dq dt is equal to dq dx dx dt. Now, dq dt, that was our definition for current. If I break it into pieces, dq dx, that's a charge per length. So it's saying in a certain length of wiring, how much charge, how many mobile charge carriers do we have? We really want that in terms of coulombs per meter. So I can use the dq dt, and then how fast are they moving? So current is proportional to V. So wherever we have a current, and we've seen this when we were calculating magnetic fields, we think of the current direction as being the direction of velocity. Well, if current, I, is the direction of velocity, what's di dt? And we can take a derivative, I got the derivative right, a time derivative, that's going to give us acceleration. So we can think of I as the direction of velocity of the charges, and di dt as the direction of acceleration. And so that says that what we've got now is current is going in some direction in that solenoid. We're calling that the positive direction, but it's slowing down. And so that's going to generate an E field in the direction, now remember that's like acceleration, the E field will be in a direction opposite the acceleration. These are accelerating electric fields that we keep talking about as the underlying effect for many of the formulas that the textbook is presenting through these chapters. It's the accelerating charges. So the charges are slowing down. That's generating an E field in this direction. Now, the reason a solenoid geometry works so well is because we've taken a bunch of wires and we run them right past each other. And we loop them around where all of these wires that are running right past each other, the current's all traveling in the same direction. And so that means that the current that is inside here is going to be generating electric fields that encourage nearby currents to keep moving. It's kind of like, come on everybody, we're going to keep moving. I know it seems like we're slowing down, but let's just push each other forward. so that we don't slow down too fast. So inductance moderates changes in current, is what we've said. We've kept saying in class. And this is how the effect works in terms of breaking it down to electric fields. Now, we actually don't need a whole bunch of wires running side by side, because even within a wire itself, even within individual wires, I've got a bunch of charges, and as those charges slow down, that's an acceleration or a deceleration, acceleration in the backwards direction. That generates an electric field that tends to push all the surrounding charges forward. Okay, and that effect is the basis for inductance. That's how inductance works, and this just concentrates the effect by running a bunch of wires very near each other. So I wrote that down. This is what's going on in this problem. Now, just for comparison, I said, what would have happened if the opposite were going on? What if this were increasing? If it were increasing, then both v and a, the velocity and the acceleration associated with the current, would be in the same direction, and that would say that the E field is opposite, and that would create a back EMF. So here there was a forward EMF, here there's a back EMF. So if everybody's trying to speed up, these forces are going, no, 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 don't speed up too fast. But if everybody's trying to slow down, no, don't slow down too fast. Let's just keep more or less doing what we're doing. So anyway, coming back to the formula, now we had introduced this idea of the EMF, or we had derived this, is equal to minus, there was a minus sign here, times the inductance di dt, and that minus sign is coming from this effect right here, the accelerating charge effect that we had talked about in class, where the electric field is opposite to the direction of acceleration. That's why we've got a minus sign in that formula. So what it says is, for the numbers that were given, which we looked at before, there is going to be an EMF pushing the charges forward of 11.7 volts from that inductor. That inductor is going to become a major voltage source in the forward direction. And that's it's not going to stop the current from slowing down. It's going to reduce the rate. It's not going to slow down as rapidly as it would have otherwise. Now, I was saying that I wanted to have a voltage drop formula that would match my other voltage drop formulas for resistors and capacitors. And to talk about a voltage drop, that's the opposite of EMF. EMF is telling us how much voltage we're building up along a stretch or through an inductor in a device. A voltage drop would be the opposite of that. So the voltage drop would actually be negative 11.7 volts. Well, if I have a voltage drop that's negative, that means I have a voltage boost. And so for this example, that's how we would interpret it. Now when we write down our formulas with voltage drops, I can just use VL is equal to L di dt, and the signs will take care of themselves. And that's what we've been doing when we've derived the formulas that we've been using for these. Now what would have happened if instead of the picture on the left with decreasing current, we had the picture on the right with increasing current? Those numbers would have changed. We now would have a negative EMF, which is a backwards effect as far as pushing, and then the voltage drop would have been a positive number saying, yes, we actually do have a decrease in voltage. Keeping track of the signs. It never goes away, right? So here's another problem from chapter 30. This is talking about energy stored in an inductor, and the approximation, it says estimate how much energy is stored. Now the approximation we've been using for solenoid geometry inductors is we've assumed that the magnetic field inside is this perfectly uniform value of B, but that the outside is 0. Now that's not true, okay, but as we've talked about in class before, but that's the approximation we'll use. So the idea here then is to use our energy density formula. I'm going to jump down to here. Energy density says that wherever I have a magnetic field, man, that number is squared. Got to get a square on that. And oh look, I squared it down below. Perfect. So it got corrected. But yeah, if you have any question here, that does need a square on it. So this needs a square right there. I plugged all the numbers into that formula. I remembered what little k is, 8.99, 10 to the 9. As promised, we have hung on to little k throughout the entire course. We have not abandoned little k. We've used it in every formula, so we can see what effect it's having. We can compare formulas more easily. Anyway, it turned out that for the magnetic value, what was the magnetic field? 0.6 Tesla, that's a pretty good sized field. 143,000 joules stored in every cubic meter. Now, the inductor is not a cubic meter in size, but that's a pretty good, well, I guess a meter would be big. Maybe it's, I don't know, 143,000 joules per cubic meter. Now, the other item we need to calculate the energy, in addition to the energy density, we need the volume, not the voltage. So make sure you're keeping your V's straight in these formulas. That's a volume. The volume for a cylinder, pi r squared times L, that is radius, that is not resistance. The volume, with the numbers given, the L's and the R's, where was the R given? Oh, there it is. L and R both there. The volume worked out to be 1.32, 10 to the minus 4 cubic meters. Multiply those together, and we came up with a value 18.9 joules of energy stored in the inductor. Now the inductor, they told us, it's about 40 centimeters long, so maybe here. And then it's just a few centimeters in diameter. So that's actually a pretty good shaped inductor for this problem, because the length is pretty large compared with the diameter, and that means it will have a more uniform magnetic field. All right, okay. Here's another problem from chapter 30. So this is 29 now. We've introduced it, at this point we've introduced inductors. There is the inductor. Here is a resistor. Here is a voltage source, a battery. And what we're going to do is we are going to charge the inductor. I like to call it charging and discharging. So I can think of it kind of like I do with capacitors. Right, with capacitors, it's pretty clear we're charging and discharging the capacitor. We're not really charging and discharging. What we're doing is we're energizing and de-energizing. Sounds like the Star Trek transporter system or something. Anyway, we're going to energize the inductors, and then we're going to de-energize them, remove the energy out. And we've got formulas for all of this, so we just have to make clear how the setup works. And so here's the battery, and we got a switch here, and I'm going to be able to charge this, energize it. And what energizing means is that we're going to be able to bring the current up to some steady value. And the steady value we're going to bring it up to is V over R. And with the numbers given, that's 5.54 milliamps. That's a little disappointing. I was thinking we were going to get more amps than that. It's only a few milliamps of current that we're going to start off with. Now, once everything's running at a nice steady 5.4 milliamps, we're going to move the switch to the other side. Now, this has to happen instantaneously. With inductors, it's a little idealized as to what's happening here. With capacitors, we could disconnect the capacitor, and the charge would stay on the plates. And that meant we had the energy stored, and we could wait around. We could go off, have lunch or something, and come back, and the energy was still stored in the capacitor. With the inductors, that's not going to happen. With the inductors, the energy that we have in an inductor is going to depend on the current. So we're going to have to know how much current we have operating. And when we open up that switch, the current stops. The current's not going to keep going. So the current that we had going through the inductor won't continue unless we have we've jury-rigged things in some fashion to where the current continues to flow. So this switch has to take place instantaneous. It's largely kind of idealized that we would be able to do this. So anyway, we used the formula for the time constant. We found out that was really short, 8 microseconds. Here's the current we're starting from. And by knowing, I guess what they wanted in this were formulas for VR, the voltage across the resistors. If I get up my voltmeter and measure the voltage here, I set up a voltmeter here, I set up a voltmeter here, and then I monitor those to see how those voltages are changing as functions of time. And what we found for inductors is that I, when they're energizing, is given by this flipped over exponential, and when they're discharging, the current drops off like this exponential. So when we throw that switch, initially at least, the inductor will be at the voltage that the battery was at. So initially, we'll have voltage across here, and then what will happen then is that the inductor will keep driving current through here, and it'll gradually drop off. And the more inductance we have, the longer it's going to take for that circuit to settle down. The current will take a longer amount of time. So let's see how the voltages are varying. And for these, I've just brought in my voltage drop formulas. For V in the resistor, that was R times I. And for the inductor, that's L di dt. Now, for R times I, there's my factor of R. And then for I, I'm going to plug in, not that one, the lower one, the discharging formula, the one right there. And I plug that in, I naught e to the minus t over tau. Now, R times I naught, if we go back to here, that's the same thing as the voltage on the battery. So what's going to happen with the voltage across the resistor is that the voltage across the resistor will start off at 12 volts. Well, that's what it was before we threw the switch. So the 12 volts is going to stay here. But what we find then is that for the inductor is going to be at negative 12 volts when that happens. When we had reached a steady current, the resistor was at 12 volts, the inductor was at 0 volts because di dt had gone to 0. The current had reached a steady constant value. Di dt was 0, no voltage here, all 12 volts here. But when the battery is out of the picture, there is now a 12 volt difference between these two ends on the inductor. There's current running through the resistor. And as long as there's current running through the resistor, we'll have a voltage drop. And that voltage drop will show up as an equal but oppositely oriented voltage drop across the inductor. So for this, I needed di dt, so I had to take, and I didn't write this separate, but I took di dt of this expression. That brings out a factor of 1 over tau with a minus sign on it. So there is my minus sign, there is the factor of tau, and here is the I naught e to the minus t over tau. If I take the expression for I naught, which is V over R, and the expression for tau, L over R, the R's cancel, the L from tau cancels the L from the formula, and all we're left with is V, which kind of has to be the case. We have to be able to get the voltages of these components written in terms of the voltage of the battery, because it's the voltage of the battery that set everything up initially. And so what's going to happen here is the EMF being generated in the inductor initially, I'm going to say is opposite the voltage drop. It's going to be 12 volts. So at least initially when we flip that switch, what that does is it takes the 12 volt drop that the battery was providing and creates a 12 volt drop across the inductor, but in the direction the current is traveling, which means it's a 12-volt boost. So the inductor is now at a point where it's a 12-volt boost. If we look at the VR and VL, that voltage in the resistor is going to drop off exponentially, and the voltage across the inductor. But at each point, the voltages will measure equal and opposite values. They'll add up to be 0, which is what you're going to expect for the circuits the way they're set up. Okay, let's see. Is this the last problem? Ooh, we might go over a bit. I apologize for that. This is an LC circuit. And again, what we're doing is, well, in this case, we're following energy. Remember in the LC circuits, we took the battery out. We said that actually becomes complicated if we put a battery in. And the reason why is an ideal capacitor and an ideal inductor, they don't lose any energy. So at least if we're treating these as ideal devices, this circuit isn't going to, it's not going to lose any energy. If we charge the capacitor and get this thing initially charged, which is what this is showing, with some amount of charge, Q naught, then the energy is going to oscillate back and forth between the capacitor and the inductor. Now, in reality, there are going to be losses. So there's going to be losses in the wiring. The wire's going to have some resistance to it. That's going to tend to dissipate energy into thermal energy. And then also, we haven't looked at chapter 31 yet, but whenever we have accelerating charges, or we have looked at chapter 31, whenever we have accelerating charges, those are going to radiate energy through electric and magnetic fields. So accelerating charges radiate energy away. So two sources that we know are going to be dissipating energy in here, radiating electric and magnetic fields, and then also the resistance in the wire. We're neglecting both of those, saying they're small effects. We really can't, well, anyway, we're going to neglect those. If we do that, then we can get formulas for the Q and the current as a function of time. We can write down energy formulas. Now, these are the energy formulas that we have developed, one back in chapter 24 with capacitors, and one in chapter 29 with inductors. Or maybe that was chapter 28, we had already introduced those. Let's see. So if we look at each cycle in terms of charge, we've chosen to use a cosine function for that, and then that means a negative sign function for the current. And the reason for that is they said at t equals 0, consider that the charge on the capacitor is Q naught, and that the current is 0 at that instant. Now, when we've taken the derivatives, what we can show is I naught is equal to Q naught times omega. So if we write down the expression for the total energy in the system, we can either write it down as the total energy in the capacitor at the instant when all of the energy is in the capacitor, or we could write it down as the energy in the inductor at the instant when all the energy is in the inductor. When Q is equal to Q naught, the current is 0. So that would be a situation where all the energy is in the capacitor, and then vice versa. When the current is at its peak, looking at those graphs over there, when the current's at its peak, Q is equal to 0, and all the energy at that time is in the inductor. So we've got those varying, the energy in the capacitor, like a cosine squared function, energy in the inductor, and yes, we can go in and show that these coefficients out front are equal. We'll call those U naught. So this would be U naught, the total amount of energy in the circuit, and the capacitor has this cosine squared effect, and the inductor the sine squared. And cosine squareds and sine squareds added together equal 1. So they're kind of complementary components of the total amount of energy in the circuit. So in the problem, what they wanted us to do was find a time at which the two energies matched, when each, the capacitor and the inductor, each had half of the energy. Now, looking at these cycles, so I started off, this is one cycle each. notice that when the charge goes through one cycle of charge orientation, it goes through two cycles of energy. And the same for the current. When the current goes through one cycle of current variation, there's actually two cycles of energy. And that's because, here the capacitor is fully charged in one direction, but here it's fully charged with the opposite charges. And in terms of these cycles, we want to be able to keep track of that. Having the capacitor charged with this plate positive and this plate negative is different from having this plate negative and this plate positive. But in terms of energy, that doesn't matter. So I'm going to get an energy, with current for example, I'm going to get an energy peak here in my inductor, and I'll get an energy peak here in my inductor. So that's going to depend, we're going to end up with, rather, that there's two peaks of energy for each cycle. So that means that the energy, let's see, that's 1/4 of a cycle when the energy has gone to 0. Halfway down would be 1/8 of a cycle. And so I'm going to write that T as 1/8 of a period. That's the amount of time until the energies match. So the energy will match at 1/8 of a cycle, 3/8 of a cycle, 5/8 of a cycle, and 7/8 of a cycle. At those 4 times, we're going to have the energies 50% in the capacitor, 50% in the inductor. Okay, and then I went through and looked at these arguments, the omega t's here. So the omega t here, I set that equal to 1/8, or the time, rather, equal to 1/8 of a period, and then showed that omega t is equal to pi over 4, and the cosine of pi over 4 is 0.707. So about 71% of full charge at that time. And then in terms of the current also, similar calculations, and that shows that the current at that time is at 71%, 0.707 of the peak current. So, the square root of 1/2 times those peak values represents 50% of the energy. Why isn't it half? Well, it's because the energies depend on Q squared and I squared. Okay, so that's what we're seeing. All right, I think this is the last problem. I apologize, we have gone over maybe 5 minutes or so. Let's squeeze this one in as long as we're here. If you guys want to pause and come back. We're going to do one last circuit. It's the LRC circuit. Here we have an inductor or a resistor and a capacitor. We don't have any power supply. So it's kind of like the last problem with the LC circuit. We are not considering any power supply to be present inside here. But they are saying that the resistance is small. The resistance is less than 4L over C. In fact, they say much less than. As long as the resistance is less than 4L over C, square root, that means that we will have oscillations. If you remember, if the resistance gets to be pretty large, we don't have oscillations. We just have an exponential drop-off in the circuit. So you can think of this as an LC circuit from the last problem, where little by little we start to take energy out of the cycle. Now, what they told us here, it's not such a small amount of energy being taken out each cycle. It actually says if the energy comes out, 25% of the energy is lost each cycle compared with where it started. So after one cycle, you'll be at 75%, 0.75 of the original energy. After 2 cycles, you'll be at 0.75 times 0.75. And then 0.75 times 0.75 times 0.75. So it's not that the energy is dropping off linearly, it's dropping off exponentially. Now, we can see that when we look at the formulas that they have given us, or that we have derived. I guess we've done a little of both. We've borrowed from what they've written down, and we've derived some of this a bit on our own. But the equation for a circuit like this, where at t equals 0, at t equals 0, we want q is equal to q naught and I is equal to 0. And the initial energy then would be 1 over 2c times q naught squared. Now, the formula they gave us in the book looks like this. It doesn't have this sign portion present. But it turns out, if I don't put this in, the current's not 0 at first. And so I think we talked about this in class. We may have even gone through the derivation. But in any case, I'm going to add a little bit of sign on. Okay, it turns out this is not a huge amount for low r. R is related to gamma in this. Yeah, it is gamma, right, that we're using. And so, and that's the book's notation. So gamma over omega is a small piece. And so to a good approximation, you can ignore this sign piece. But by putting it in and taking a derivative here, you can show that the current then is given by this expression. So we want the current to be 0 when t is equal to 0. And by setting t equal to 0 here, the current goes away. If I don't put that sign portion in and take a derivative, I end up with sine and cosine contributions here. And the cosine piece does not go away at t equals 0. Okay, so these are more complicated than just sines or cosines. Putting this extra exponential factor in makes a difference. So, you know, you're not required to derive all this. If you've seen this in other classes, say differential equations, and you're curious about how this all works, by all means, take a derivative of this expression and show that this is what you get. And we want something that goes to 0 when t is equal to 0. Okay, now for us, what we want to do from this is say, look, the total energy is proportional to q squared. In fact, when we first start out, the total energy is 1 over 2c times q naught squared. And we're going to say that's roughly given by the exponential factor. That's not quite true. So if you do a very careful analysis of the rate at which energy is dropping off, there's a little bit of an oscillation effect to it. It's not dropping off at a purely exponential rate. But again, it's, you know, they told us the R value is really small, and so for the R value being really small, we can neglect the terms that, we can neglect this sine term here, and then square both sides, and ignore this factor, well, roughly reduces to omega. Anyway, what we can do is say that it's dropping off, the energy is to a good approximation, dropping off like the square of an exponential. And then what we want to do is introduce an energy fraction. So the energy I have after a cycle goes by is going to be equal to the energy I had when that cycle started. So this is after well, we could write it this way. If this is the nth cycle, then this is the n plus 1. So every time I go through a cycle successively, we're going to have the energy drop off by that factor squared. And so I'm going to set that equal to a fraction, which is my 75% fraction, equal to this. And then I'm just doing a bunch of algebra. I'm taking a logarithm of both sides and solving for t, because what they ask us to do in the problem is find the value of time at which the energy has dropped to a certain fraction. And so that fraction they gave us was 0.75, but here is the general formula that we've derived. So if you tell me what fraction of the energy is left, I can tell you how long it's going to take until we get there. And so for this problem, 0.75, the ln of 1 over, I did the ln of f. I've got to check that too. I think this is the ln of 1 over f because the ln of 0.75 would be negative. So that's a 1 over f, 0.288. I can, oh, that was the formula though, huh? I guess there's not a lot to be done more because they did, yeah, that's what happened. So they did not give us values of L and R. So we just don't have those. So I think that's why I prefer just leaving it in, well, that's in terms of the time constant. And then the time constant for an LRC oscillating circuit is 2L over R. I substituted that in. So either in terms of the time constant or more directly, this formula where if they give me L and they give me R, I can figure out how long it's going to take. We didn't need C, which makes me a little suspect, but we didn't. Turns out that didn't show up. Does not come into play with the exponential drop-off. Interesting. That's an interesting observation. Okay, we'll stop. We are like 15 minutes over. I really apologize for that. Maybe the next one will be shorter. Maybe not. Anyway, have a good rest of the day. If you guys have questions, definitely stop by and we can take a look at those. Good morning. All right, it is time to do some more reviewing. You guys might notice that this is similar. There was another review that we did with chapter 29 and the first half of 30. This review is going to be the second half or the last half of 30 and 31. The last time I tried this, I went over about 10 minutes. Sorry about that. But this one I think will be shorter. I know, I always say that. But I really, truly, honestly think this one will be shorter. We'll see. In any case, we're going to be looking at AC circuits. That's the second part of the later part of chapter 30. So let's go ahead and let's get that set up.